So, welcome everybody. Welcome to today's seminar. We thought we'd give you a bit of an overview of a lot of activities that have been going on. It's one of the Climate Energy College seminars. I'm Malte Meinshausen. And before we get properly started, let me acknowledge the traditional owners of the land on which the seminar would normally take place in the Climate and Energy College in the Grattan Street, the Wurundjeri people of the Kulin Nation and the elders past and present. It's a great pleasure to have you here today, and we are looking forward to soon in the new year, now that everything turns more rosy again and the bad part of 2020 is over, that we soon in the new year have you somewhere in a physical seminar space as well, although the online seminars also have some great advantages. Anyway, thank you for being with us today. As I said, I'm Malte Meinshausen. I'm have been with the Climate and Energy College from the start. Now it's led by Professor Peter Rayner, and I'm also IPCC Working Group 1 lead author for the forthcoming AR6 assessment report that originally was planned to come out in April. Now it's slightly deferred thanks to COVID to August. And then I'm also one of the co-writing team members in the synthesis report that is coming out in 2022. We did a lot of work on climate projections also as part of the IPCC, ongoing IPCC process. And here today you will see a bird's eye perspective of some of our activities. And I'm glad to have with me the two powerhouses here behind lots of the work, which is Zebedee Nicholls, who does his PhD on reduced complexity climate models and their intercomparison, and also Jared Lewis. He has been working with Boudica Scientific in New Zealand before he joined a couple of years ago us at the Climate and Energy College. So us three, normally internationally seen as the MAGICC gang, because we mainly work with a MAGICC climate model, apart from other activities. We will give you that bird's eye perspective. And yeah, please use the chat function, which you see below. And please use also the Q&A very actively. We are going to monitor that. And after our slide presentation, we are going to hopefully have enough time to address all the questions. We can also stay a little bit longer if there are lots of detailed questions. Again, we don't go into too many details, but we would very much appreciate, if you want to know about them, that you ask then more about it. So our quick overview of today is I just say something about scenarios in very general, and then also the work on the greenhouse gas concentrations, both the historical data sets and the future. Then we have a great tool that you can use also for your research, or just to have a look on the tool for exploring CMIP6 output that is presented by Zebedee. And Zebedee also then goes into the probabilistic reduced complexity model, MAGICC, and how to encapsulate uncertainty. And then we close the presentation by an interactive tool that we present to you actually for the first time today, which allows you to set certain parameter values in that probabilistic setting and look into the scenarios in the future, how the temperatures, global mean temperatures up to 2050 or 2100 actually change if you change climate sensitivity or TCR. So here, two excellent tools and a little bit of background. Everything now starts with Trump, and we try to move away from it. So here the outline of today's seminar. We first have some general notions about scenarios and Trump. Then more specifically on the SSP scenarios, the greenhouse gas concentrations that we provide for the SSP scenarios. The Earth system models is then the part talked by Zebedee and the tool, where we have our visualizer, and then going from the Earth system models to the probabilities, our probabilistic MAGICC 7, and then in the end, the portal. So starting first here with a view at the annual energy consumption in the US. First point is here, the coal is not only in the US, but also globally on the way out. The latest IEA projections also project a slightly decreasing coal demand globally, even in the absence of further climate policies. So I think that is a very promising tool. Unfortunately, some countries are still placing emphasis on gas. Gas as a transition fuel maybe could be considered a transition fuel 20 years ago or 10 years ago. Now we are so far into the remaining carbon budget that gas cannot be regarded a transition fuel. Gas has just roughly half the emissions of coal, but still it's 50% emissions too much. We really need to focus our investments towards the net zero goals that so many countries now adopt. And yeah, you see here in the US, gas is rising quite substantially. That's certainly a trend in the wrong direction, and also oil, maybe here with the electrical vehicles boom and the Biden-Harris plan that might hopefully go in the different direction, but we shouldn't make any mistakes. The Biden-Harris plan and the net zero goal by 2050 requires some oomph and a lot of longevity in the policy design. Here you see a nice graph by Glenn Peters. Every 5 years, the election cycle in the US, and here the goal for net zero by 2050. So that these policies to drive down emissions and capture the opportunities of the energy transition, they need to be carried on from administration to administration. Now, one general point, again, from the start, we often see in the climate change literature the RCP 8.5, which is a very high warming scenario. And against that, we contrast some other scenarios. There has been some people made increasingly the notion that these very high worst case reference scenarios, they can't be excluded, but they are not the most likely reference scenarios anymore. And actually with the new design, the new framework of the SSP scenarios, we make it quite clear that the highest scenario is not the scenario that you should compare everything against it. In a different world that is either regional rivalry or sustainability, we will have reference scenarios. So what if we don't do any further climate policies that are quite a bit lower? And with the renewable energy costs coming down and that economic motor behind the decarbonization of the electricity sector, we actually look at the moment at the most likely reference case scenarios that are almost stable in global temperature. So that's a very good signal. And that is what you see here in that blue line from the IEA, just the 2020 report that came out recently. The COVID here, you can almost see it make the slight dip here with the orange line if you have recovery plans. But on COVID, I think the main notion that has to be said is, yes, there's a slight dip in emissions, but it doesn't make a difference in the long term. However, what could make a big difference is the COVID recovery plans, the trillions of dollars that are poured into COVID recovery globally. If only a fraction is put into the additional investments necessary to drive down fast the emissions in the electricity and the transport and other sectors, then we will achieve the 1.5 and 2 degree goal as a side effect of these tremendous and much larger COVID recovery stimulus plans. So these were the general points. Now a bit more onto the greenhouse gas scenarios here. There are basically 2 papers here that I'm talking to, and you see here the links also in the bottom. We share the slides later on our website, so you can have a look. First, on the general scenarios, you have different scenarios. You have idealized scenarios, and then you have these multi-gas scenarios that really tried to map the future. And so in terms of mapping the future, you have in the new generation, which are called the SSP scenarios, you have 5 different broad scale socioeconomic development features, from sustainability, regional rivalry, inequality, high fossil fuel development, and a middle of the road scenario. And what you see here roughly indicated as these black bars is you can have a lot of different temperature outcomes depending on how much mitigation action you combine in these worlds. But in some worlds, like the sustainability world, even if you, unless you put money in your hands to burn fossil fuels with additional resources, you won't get that high as, for example, in a fossil fuel development world or in the middle of the road or regional rivalry case. So these 5 large socioeconomic development storylines span kind of the future. And then depending on your mitigation action, you get either to the here very low 1.5 degree pathway or 2 degree pathway or something in the middle. We talked briefly about the reference scenarios. So there are different reference scenarios, and that's, I think, an important step forward in the international scenario literature. And then we have now also in the SSP framework an unprecedented amount of mitigation action assumed. In the RCP world, which has been the last generation 7 years ago of scenarios, we only went down to 2.6. Now, luckily, we also have a scenario that is consistent with the 1.5 degree target. Here, what we did in preparation for the big Earth system models to run with these different scenarios is we compiled a lot of historical measurement points. For example, Cape Grim, as a CSIRO, has a fantastic station that samples the air and determines a lot of greenhouse gas, the mole fractions, and we just put it all together, binned it, and also here big thanks to Elizabeth Vogel, and I should also thank a lot of other people that have been behind the scenes to do all this work. You see that on the top slide, but anyway, we have here the historical data sets, and then we combine it with our MAGICC model to project the future concentrations of these gases here: CO2, methane, nitrous oxide, and a set of 40 other greenhouse gases that we project with MAGICC. And then the Earth system models across the world are going to use that as an input to run these future scenarios. Here in the lowest scenario, the SSP 119, roughly consistent with a 1.5 degree target, you see CO2 concentrations come down to roughly 350, which then on the radiative forcing axis, where you can compare all the gases, roughly looks like this. So you have a bit of methane, a bit of nitrous oxide, and then the other gases. Also some interesting factors here, because nitrous oxide has such a long lifetime compared to methane. You see that nitrous oxide here share increasing over time, where this methane is more important right now, but then in the long term, it will be nitrous oxide thanks to the long lifetime. Now, this is for the lowest scenario. Let's have a look at how the next lowest scenario, the roughly 2 degree thing looks like. Here, we just simply won't come as much down with the CO2 concentrations and the CO2 induced radiative forcing. And then when you look at the other gases, this is in the other scenarios, this is roughly a scenario that is in line with the current nationally determined actions under the contributions under the Paris Agreement. That would roughly get us to 2.5, 3 degrees. And that is, here you see the share of future warming induced by these well-mixed greenhouse gases. And then, of course, it can go much worse if you look at reference cases where, let's say, Trump would govern the world, that he would be more in this realm. For example, the SSP 370 case, or then the highest scenario is the SSP 8.5 case with maybe just about 4 or above 4 degrees climate change by 2100. And then the highest models here is up to 17 degrees of warming by 2300. Anyway, now, the one key thing that is coming out from CO2 being so important, and luckily we have a very good understanding of how CO2 influences temperatures, is that we have these remaining carbon budgets. Now, many countries, many states want to define their targets in terms of greenhouse gas baskets, as under the Kyoto Protocol or the Paris Agreement. And that is very easy. There's a very easy way forward, because from the CO2 budget, you can easily defer a greenhouse gas budget, whatever metric you use, because if you look at the realistic scenarios, how they pan out, then it's just a little bit on top of that if you want to have a greenhouse gas budget. And we showed that, for example, in a paper here that we did for the Victorian government to define their strategy for their net zero goal. You find the link below. Now, I won't go into detail here because I'm already going over time. But you will find on our University of Melbourne website, here you will find all the background to these greenhouse gases, these 43 well-mixed greenhouse gases. Here I just show the CO2 fact sheet for SSP 119. You see here the seasonality, the latitudinal gradient is captured, and then how it changes over time. when we suck out CO2 from the atmosphere, again, the latitudinal gradient might actually change from normally northern hemisphere having higher concentrations to then, if we draw CO2 down in the northern hemisphere, to northern hemisphere having lower CO2 concentrations. And here, for example, you see all the historical measurement data points with a lot of variability, but we distilled the global mean and the hemispheric averages out of here. And yeah, there's a lot of detail in there, and I'm happy to go into detail if you have specific questions, but we have lots to cover now. So here, this is my last slide. What do the Earth system models then do with these inputs? And so greenhouse gases is only one input. There's aerosol emission fields, there are ozone fields, there are solar and volcanic forcing series, and they are then all driving these models by around 40 odd modeling centers. So for example, the Australian Axis model is a very well regarded one internationally. It always produces very good outputs that compare well against the observations. It's one of the 40 global modeling groups. And then these big models, they have to first pass so these so-called DEC simulations, and then they can take part in a lot of different experiments. For us, most interest are these scenarios, because we want to figure out what is climate change going to look like over the 21st century, and therefore we need these Earth system model runs, and we need a bit more to what Zebedee is also talking about. We can't only use the Earth system models, but these are absolutely key and pivotal for that. Now, the slight entry hurdle for any researcher or more the layman is that there are massive data sets coming out of this CMIP6 experiment. As you might know, they're all NetCDF. Not everybody's familiar with NetCDF formats, lots of acronyms, lots of sliced files that need to be glued together somehow. And with that, I hand over to Zebedee, because we provided now a tool with which you can easily access lots of the CMIP6 data. It's one of the very few, if not the only tool that provides you these aggregated CMIP6 time series in such an easy fashion. And now I hand over to Zebedee.
Thank you, Malte. Malte, do you want to keep driving the slides, or shall I share my screen instead? Great, beautiful. Okay, so thank you for that introduction, Malte. So in the next 15 minutes or so, I'm going to cover basically two key parts of this timeline Malte set out. So firstly, our CMIP6 data visualization portal, which we've put together. And then I'm going to talk about how we go from these CMIP6 model runs through to probabilistic climate projections, and what the difference between the two is, and why we think this is an important and key step in the scenario assessment work that's being done around the world. So the first thing to look at, thank you, is that CMIP6 output, as Malte said, can be fiddly to deal with. So in general, you've got to deal with at least gigabytes worth of data. In the worst case, you've got to deal with terabytes worth of data, and it can be extremely hard to get your head around. As Malte said, there's lots of acronyms. You don't just get a single file which has everything you need. You've got to deal with multiple files, join them together, work out what goes with what. It can be fiddly. So what we've done is we've provided a tool which kind of does this all for you. And the motivation here was that for us to do our reduced complexity work, which I'll come to in the next part, we needed all of this data kind of pre-processed. And we thought, well, we've gone to all this effort, we may as well make it available for other people to use so they can skip the headaches that we dealt with. And that work's been submitted to Geoscience Data Journal, and it's under review at the moment. And we hope that it will come out in the next couple of weeks to a couple of months. So as you can see there, the link's on the screen. That website is live at the moment. With one caveat, we're doing a few upgrades, so it can be a little bit temperamental. But when the paper comes out, that'll all be polished and ready to go as well. And we'll make sure to publicize that widely. So a couple of disclaimers before I move on. We obviously don't provide the entire CMIP6 archive, because that would require dealing with petabytes of data, which isn't something we really want to do, and we don't think anyone else wants to do. So we focus on monthly data and annual means. And then what we pull out is high-level spatial aggregations. So we don't provide time series, for example, of just Melbourne, but we will provide time series of Southern Australia or Eastern Australia or the global mean. And I'll show you a few of those in a minute. Next caveat is that if you use our data, you've also got to abide by the CMIP terms of reference. CMIP is the key organizing body for model comparisons of the Earth system models, which we rely on, and they put a heap of work in. So if you do use the data, please make sure you also abide by those terms of use. And then the final one, which I've already mentioned, is we're doing a few final revisions, and we're going to finalize all of this in the next few weeks or so. So what have we done? What we do, and I'm going to talk through this in a bit more detail in a second, is we take the raw CMIP6 data, so that's in the bottom left corner down here. We combine it with some masks, and I'll talk through what those are in a second, and we spit out time series. So for example, in the top left corner up here, you have the global mean signal from this particular set of data, or you might only want to look at the Northern Hemisphere land, or only land regions of the world, or only ocean regions. We can see here quite nicely that in the land regions, you have much higher variability. The oceans with their much greater heat capacity are much more stable. And so we pull out these regions of interest to us. So the way this works is we start with the raw gridded outputs from CMIP6. So each of these maps is a time slice of output from a CMIP6 model. So you can see that we start all the way back in January 1850, then we look at February 1850, March 1850, et cetera, et cetera. And in this particular case, I think we end up in July or December 2014, for example. And so we then go over all of these maps and we do some processing on them to create time series. So for each of those maps, we'll take the region of interest. So we might be only looking at land regions of the world. So you can see here that the yellow and bluish plots are the bits we're looking at. And I'll come back to what the color gradient actually means in a second. And the purple bit is the bit we're excluding. Or we might take the global mean, in which case we cover the entire Earth and consider the entire Earth. Or we might only look at the ocean regions of the world. So instead of blocking out the oceans now, we're blocking out the land regions, and we're taking our means over the ocean regions. We can also do smaller regions. So for example, we might only look at the Greenland ice cap. So we block out everything except for this little section up here, which is over Greenland. Or we might even look at Southern Australia. So we'll block out all of the world except for Southern Australia, which is this area you can see here. And in the maps you can see the grid's obviously quite coarse. So these blocks actually look like squares. When we do this for real, we use a much finer grid. So these actually look smooth in their contours rather than being quite so obviously gridded. We also provide, so these regions follow what are kind of being colloquially called the AR6 regions. And those were published in a paper by Nicholls et al. In Earth System Science Data. And they define these regions, which you can see on the right. So we've got the Greenland ice cap up the top, and then they cut the globe into, I think it's about 35, maybe slightly more regions. And we've processed data, or we've processed the data for each of these regions. So we've got our raw CMIP6 data in the bottom left, which we've spoken about. And then we combine these with area weights. So it's really important to weight the contribution of each grid cell by its area to make sure that you actually get some sensible aggregate time series. And then we also use the surface fractions. So for example, if we're looking at land data, not every cell will be either completely land or completely ocean. Some of them will be a blend, and we want to take that information into account when we're calculating our mean over all the grid cells of interest. So we combine these area weights and the surface fractions with our masks of interest. So whether we're looking at, world, land, Southern Hemisphere land, etc. We take a weighted mean over all the cells, and then we do that for every single time slice, and that provides us our time series. So to produce each of these time series here, we need to touch at least a gigabyte's worth of data. And in some cases, we're looking at more like hundreds of gigabytes, especially for some of the more complex ocean grids. So it's some pretty serious data handling, and it can be a bit of a pain in the neck. And we're hoping that this data portal removes some barriers which traditionally exist. So what do we actually end up with? So here's an example of global mean temperature projections from CMIP6. And here I've taken SSP 119, so the roughly 1.5 degree scenario, SSP 126, which is the roughly 2 degree scenario, SSP 245, more or less in line with the nationally determined contributions. and then SSP 534 over, so this overshoot scenario. And at the moment, you can't see very much because it looks like spaghetti and soup, but we're working on some extra coloring options. But if we, rather than looking at all of the models, let's say we just look at the access model, the Australian model, we can then start to see some more interesting bits and pieces. And all of this can be done through our web portal. So this cmip6.science.unimelb.edu.au. So here I've just pulled out access simulations for the same scenarios. And these could be used, for example, to try and inform some assessment of warming under these different scenarios. And one thing I noticed here is that the Access CM2 model is slightly warmer than the Access ESM15. So the ESM15 is a system model, has an interactive carbon cycle, whereas Access CM2 doesn't have that interactive carbon cycle. And it looks like Access ESM1 is slightly cooler in this SSP245 scenario, but in the lower end scenarios, they're very similar. So if someone at Access has probably worked this out why this is already, but if they want to flick across any information, I'd be very interested to hear what's going on there. Then the second thing we can do with our portal is compare CMIP6 and CMIP5. Now, again, we're going to start adding some coloring to the website, but I've done a bit of that offline, so it's a bit more obvious what's going on. And one of the things you can do is actually compare the SSP scenarios, so these CMIP6 generation scenarios, with the RCP scenarios, so CMIP5. And we see that it's pretty clearly that the SSPs in general are slightly warmer. So this dark blue line here is SSP 126, and this royal blue, for want of a better term, is RCP 26. And we see that the CMIP6 projections sit higher than the CMIP5 projections. And it's a similar pattern for SSP 245, this yellow line up here, and RCP 45, this blue line in here. And really, the key point here is that all the data to make all of these plots is accessible now. And so if you want to do this sort of exploration, we really encourage you to go to the data portal, download it, and start slicing it and cutting it. I would estimate that we've touched about 30%, or looked at about 30% of the data that's on there. So there's a heap more available if you want to go and do exploration. And there's plenty of insights in there that we haven't worked out yet. So if it is of interest to you, these kind of monthly, annual mean, high-level spatial aggregations, all the data is there, and we encourage you to go and play with it. I'm just going to flick over these next couple. So we can look at, for example, regional warming here. So we can see that Eastern Australia warms at about the same rate as the global mean under SSP 26, I think this one is. Whereas the Greenland ice cap is projected to warm much faster than the global mean. And that's been seen before, but now we can see what CMIP6 models, so this latest generation, are actually saying. We don't only do temperature, we also do other variables. So I've just pulled out ocean heat uptake here from a bunch of different models. And so that you can go well beyond temperatures with the data set that we've crunched. And that's certainly an area that's ripe for exploration, especially in the carbon cycle. So to kind of pull this together, all our data is freely available to access and use via the portal. Just keep in mind the CMIP terms of reference. There's a search functionality. Then we have some quick plots to just make sure you're getting roughly what you want. And then you can download it, from which point you can do whatever you want with it. We provide it in a text-based format. So if you want to read it in Excel, you can do that easily. If you want to read it in Python, any other programming language, you'll be able to do that without the headaches of having to deal with NetCDF and binary data, which can be tricky at the best of times. We also have an API for those of you who don't like clicking buttons and want to use an automated download process. And then we're working on some custom plotting galleries. So we have some examples of how we deal with this data, how we slice it and dice it to do different bits of analysis. And one of those, which is pretty common, is calculating the equilibrium climate sensitivity from all the CMIP6 models. So there's a lot of talk about this ECS measure, and often it's not clear how it's been calculated. So we've just got a notebook there which goes through how you actually do this for all the different models and shows you some of the data that sits underneath, and it means you can live update as more data comes in if you so wish. So that's our CMIP6 data portal, and we use that to then inform us and to be able to go kind of in some sense beyond a multi-model ensemble. So the multi-model ensemble from CMIP6 is a key cornerstone of our climate science research, but it can't answer every question. So for example, what I've done here is taken projections from all the models for the SSP126 scenario. This is nominally a 2-degree scenario. We can see here there's quite some disagreement amongst the models. So we've got some models projecting only 1.5 degrees of warming by the end of the century, with other models being up at 3 degrees. And so the question we might ask ourselves is, okay, how do we make sense of these model projections? You know, should we just take the mean over all the models and that's our best estimate, or the median? How much uncertainty is there? And one thing we could do is say, okay, well, let's start off by looking at how the models perform over the observational period. So 1850 to 1850 to today, 2019, 2020 roughly. And we might say, all right, we'll use this as a benchmark. So if we add observations on here, we can see that in general, the multi-model mean, or the models sit roughly in line with observations, but in the recent period, there's quite a few models which are warmer than observations. So this might cause us to think, well, if we use the multi-model ensemble from CMIP6, perhaps we're biased slightly too high and our projections will be slightly too high. So people have all sorts of ways to get around this. And I'll just repeat the point that the CMIP6 multi-model ensemble is a key pillar of climate science. So this is not trying to say that it shouldn't be used, but this is trying to build on top of that multi-model ensemble and see what else we can determine. So for probabilistic projections, it alone is not our tool of choice. And so there's different options people take. And one is to try and constrain the ensemble with various post-processing steps. There's a bunch of papers which have done this. We go for quite a different approach, which is to use a reduced complexity climate model. Now, I'm going to skim over some of the details here. Actually, MAGICC's reduced complexity climate model, and we really focus on global mean output. And the reason that's helpful is that it makes MAGICC really, really fast. So we can explore uncertainty and probability in a way that CMIP models can't. MAGICC's a parametric model. So you define its parameters and then that defines its, or changes its output. So here I've just taken 3 different values of the equilibrium climate sensitivity, the ECS, and they give you 3 different projections. So the lowest one here has the lowest climate sensitivity. The middle one here has a climate sensitivity of 2.9, so roughly in line with most understanding. And the one at the here has a climate sensitivity of 8.4, so really, really at the high end. And we can see that just changing this one parameter really changes MAGICC's response. So the question we ask ourselves is, well, what are sensible parameters or parameter values for MAGICC? And the way we do this is we compare with observations. So for example, if we put observations over the top here, we might say that the very low climate sensitivity line, so this one at the top here, has, and this is slightly counterintuitive, but we'll come back to why in a second, is kind of at the top end of observations, and then the other 2 lie with more agreement. So we might say that these 2 combinations, which are closer observations, are more likely parameter values. And what we do with MAGICC is we try lots of parameter value combinations, not just varying the ECS, but also varying aerosol response, carbon cycle response, other greenhouse gas cycles, radiative forcing parameterizations. And we go over lots and lots of combinations. So we do about 20 million, and then we use a technique called a Monte Carlo Markov chain to keep the parameter values which are most in line with both the best estimate and the uncertainty in the observations. And we use observations both of global mean surface temperature, but also hemispheric temperatures, as well as ocean heat uptake. So we do all of this and we get this posterior distribution. So basically a distribution of parameter values, which tells us the range of parameter values for MAGICC, which are roughly consistent with observations. So they look a little bit like this. So we have a distribution for example, equilibrium climate sensitivity, but then also these covariances between, for example, the aerosol response and the climate sensitivity, or here the TCR is a transient climate response. And so this posterior is kind of our best estimate of the range of plausible climate system properties. But for many applications, the interest is not in using MAGICC to define those ranges, but instead to say, okay, another researcher has done, for example, Steve Sherwood at UNSW did a huge paper on what do we think the range of equilibrium climate sensitivity is, and they came up with their own range. And so what we do is we use our posterior, which contains all the covariances between the parameters, and we subsample it to match these kind of quasi-independent assessments. And by doing that, we can actually produce behavior which is consistent with some assessment, for example, an ECS assessment, but keeps all the correlations between parameters which you need if you're going to stay consistent with observations at the same time. So it looks a little bit like this. I'm going to go through this pretty quickly. We have if we look on the right, the ocean heat content. The blue here is the assessed range. The orange here is the posterior coming out of MAGICC. And what we'll do is we'll subsample this orange distribution to get the green distribution, which is closer to the blue one. We can't make it perfectly match the blue one because we also have other constraints. For example, we're trying to get equilibrium climate sensitivity right at the same time. We might be doing 20 other different components of the climate system, but we can use this to try and produce MAGICC setups which are consistent with independent assessments, but which also maintain the covariance between parameters, which is required. And so what we've kind of ended up with is a tool set, which means that we can capture different opinions or assessments of the climate system, and we can see what difference they make for projections. So if we kind of look at where we are now, Malte's taken us through all these scenarios. We've shown you our CMIP6 data portal and visualization. And we've shown how we build on those CMIP6 data to create these probabilistic climate projections. And now I'll hand over to Jared, who'll take you through a tool which actually allows you to use and explore the implications of the different of subsampling two different assessments and how that changes your projections.
Great, thank you, Zeb. I'd just like to reiterate that work that Zebedee's done is absolutely phenomenal, and we're very excited to see where that goes in the next few years, and we're likely to expect that whenever you see a particular statement about an exceedance of a certain temperature, that particular piece of work is under the hood, really driving that. Yeah. So, as Zebedee mentioned, I'm here today to talk about an interactive tool that we've produced using this kind of best-in-class science and a combination of probabilistic projections of MAGICC, as well as our ability to, which is really driven by our ability to crunch the CMIP6 data. So for large global organizations, physical climate impact drivers are becoming a major asset risk. And if you're a global organization with a geospatially diverse set of assets, a good indication of your predominant risk is global mean temperature. So we partnered with Autonomy Capital, which is a large multinational hedge fund with billions of dollars under control. And they want to be able to figure out how different uncertainties and will impact the global mean temperature in the future. So this is a kind of a really good marrying of the science that we're doing and some particular interest in the finance sector around how this will impact their investment decisions. So what they really wanted was a real science tool that's not just a really simple model, but we want the best possible science, and it should reflect the current scientific uncertainties. And most importantly, it has to be probabilistic rather than just having a few individual model projections, because that uncertainty is really important into the future. So what we did is we pulled together this particular tool. You can go to it yourself now at magic.autonomycapital.com. This is actually the first time we've presented this in public, so it's quite an interesting event, and we'd love to hear some feedback. So if I quickly jump to my screen, Malte, I will, if you stop sharing, I can share my screen and run you through the tool. Okay, so we start off here with the tool. Again, it's magic.autonomycapital.com. That's MAGICC with 2 C's. There is a little kind of introduction to what we're talking about when we introduce things like uncertainty. This particular tool is for knowledgeable non-experts. So we can have there's a few introduction slides here to get everyone on the same page. I'll skip through them quite quickly, but feel free to read this at your own time. Where we get to is this idea of there's 3 main sources of uncertainty in the Earth system. The first one being natural variability. We're not exactly sure when the next big volcano is going to hit, so we can't say with certainty what's going to happen into the future. There's a few other things such as large scale processes that we still cannot quite resolve. The second source of uncertainty is scenario uncertainty. We don't necessarily know which pathway we're going to go down. As Malte mentioned before, there is a bunch of different SSPs, and those are still, there are only a handful of pathways into the future. The actual pathway that we're going to follow isn't necessarily going to be down one of those lines, but they provide us a good indication about the possible ranges of the future. And our third source of uncertainty is our response uncertainty. That's what Zebedee was talking about, where, for example, we don't quite know what the exact value of ECS is. Each individual CMIP6 model has an inherent value for ECS, and they all fall within a range, and we're not quite sure the exact value for ECS, but we know from various studies about the potential range for it, the assessed range of it. Finally, here we kind of come to just a brief overview of the different SSPs again. In this case here, we're looking at the greenhouse gas emissions and CO2 equivalent over time. This is only a very one-dimensional slice of the real scenarios, and we really invite you to check out other papers such as Riahi et al. 2017, which describe the exact assumptions that these scenarios have in greater detail. And finally, we get to the tool itself. So while it's relatively simple, there's three main sources of data here. We have our observations. In this case here, we're using a data set called HADCRUIT with its median value as the thick line and its 1 sigma uncertainties as the plume. We have these individual lines here. These are individual CMIP6 annual mean, global mean surface temperatures, one per model for a particular emission scenario, which I'll get to in a second. And finally, we have this plume. This is MAGICC being run 100 times, in this case here, with an indicative, very likely range being shown here. So, but MAGICC is driven using the parameters that we show over here, which I'll get to in a second as well. So this particular tool is kind of the end result of us crunching through terabytes and terabytes of data and running hundreds of thousands of core hours to get to this point. We can look out to what happens out to 2100 under different scenarios. And allow to quickly assess at a very high level what the particular ranges of how the scenarios affect the final temperature. And finally, here we have the particular, we have 4 different parameters here, which are key parts of key parameters within the Earth system, for which we have assessed ranges for, but we're able to subsample these assessed ranges from Zebedee's tens of millions of MAGICC runs to be able to create coherent futures using these different distributions of parameters. So this enables you to explore how, for example, changes in the range of ECS affect temperatures. So for example, if we look at only up to 2050, ECS doesn't necessarily play much of a role in determining how the median temperature changes for a given scenario. If we then looked at, say, 2100, ECS, small changes in the actual distribution of ECS actually end up having a much larger impact. So that's something that you may want to explore. And as time goes on, we may be able to narrow down exactly the ranges of these distributions and minimize this uncertainty. Another cool feature that we have here is that we engaged with some experts around their particular expected ranges for some of these parameters. And so we're able to kind of provide, if we click on this one here, this is Yuri Roglig's expected view of the future. And he's able to, we're able to kind of engage with the expert community, and hopefully we fill out more dots of those orange dots in future. Another feature we have is this is burning embers. So these came from the SR 1.5 special report for 1.5, where we are able to see impacts on different aspects of the Earth system. For example, coastal fisheries up to 2 degrees. It starts to get pretty bad for the coastal fisheries in 2 degrees. As we all know, the coral reefs are particularly vulnerable to temperature, and we're already in this purple zone, which indicates that there is large, very high risks of severe impacts and potential irreversible impacts already at our current warming of 1.1 degrees. So all in all, we have put together a tool here that marries our ability to our CMIP6 crunching capabilities, as well as Zebedee's amazing probabilistic projections, and allows users to explore the different sources of uncertainty within the Earth system. So I'm going to quickly jump back here. So far today we've discussed quite a wide range of topics that go all the way from changes in policy through to how we end up defining different pathways into the future and how that impacts the different concentrations of greenhouse gases in the atmosphere. There's different assumptions of concentrations in greenhouse gases in the atmosphere. Finally, then we looked at how these impact the CMIP6 models and all the different model runs we do. We demonstrated our new data portal, cmip6.science.unimab.edu.au, that you can go check out so you don't have to crunch all of that data yourself. Zebedee then ran us through how we then take these Earth system models and perform many millions of runs to come up with our set of probabilistic MAGICC runs, which really explore the different parameters within the Earth system, the distributions of them, so we can have coherent ideas of the future. And then I've just demonstrated our new interactive portal for probabilistic projections. That's magic.autonomycapital.com, and that's magic with 2 C's. Thank you very much to Autonomy Capital for sponsoring that work. And we'd love to see how that goes. And now looking forward to the future, we're looking to create more and more visualization tools around how we can get better insight into the CMIP6 data. We're also exploring how our regional CMIP6 data crunching and how we can marry that with MAGICC to produce probabilistic regional climate projections. So for a much higher resolution than, say, global means. And also we're looking at how we can come up with new scenarios and how we deal with creating new sets of greenhouse gas concentration assumptions under different worlds, such as under a world where we migrate towards using more hydrogen. So I'll pass back to Malte.
Thank you very much, Jared, and thank you very much, Zebedee. And again, at this point, big thanks to all the contributors that have been involved in this work. There are the MDAP people, there's faculty science, IT, who did both tremendous work, and we had lots of collaborators on our papers, and it was great fun overall to be part of and still be part of a very active IPCC AR6 assessment cycle. So we are all huge thanks to all our colleagues there. That is the next seminar, but before we go to the next seminar, we have a few questions, and I would encourage you to ask whatever question, whether you want to ask about our take on Trump or our take on the parameter TCRE in our models, or why the low climate sensitivity case in the history was slightly warmer in Zebedee's slide than the high climate sensitivity case, which makes initially not maybe too much sense. Anyway, ask all the questions you have. And yeah, we can make you panelists so that also your video is shared, or you can just talk. So first, I would love to, if you want to ask a question, just raise your hand, as Ulrike already did. And now I would like to invite Ben to ask one of the questions.
G'day, can you hear me?
Yes.
Oh, thanks very much. It's great presentation, great visualizations. I love it. Malte, you've already answered the water vapor question, so I'll ask my RCP 8.5 question, if that's okay. I've read about this and that it was introduced as an end game scenario, as in there'd be lots more, a massive increase in CO2 emissions. And then I think some politicians get hold of that and they use the numbers resulting from that, the temperature numbers, to put a bit of fear into people. How much, I suppose, rephrasing my question a little bit, how much do your models use those extreme scenarios? Thanks.
Yes. So just to, yeah, we had RCP and a scenario that is similar to RCP 8.5, the high scenarios. We had that for all the past 20 years in climate research. They were starting from the 1990s, they're called IS92 scenarios. There were these very high scenarios in there. We have the SRS scenarios that had also that higher range, and the SRS scenarios didn't have climate mitigation in there, but there were these very high scenarios. There were also relatively low or these 3-degree warming scenarios in there. So it is to span the plausible future range. And it is not to scaremonger anyone, but if, for example, the world would have embarked on a fossil fuel intensive pathway with, for example, the tar sands in Canada being used up to the last drop, and a very coal intensive future, then that is very much a plausible scenario. Now, over the recent years, with the early investments in renewable energies, and therefore the learning curve, and therefore the costs coming down so much, these very high scenarios are not that likely anymore, because now we have the cheaper zero emission options out there, and who would spend extra money to cause emissions? We don't have anything from emissions. And so therefore, simply the economic driving force makes these very high end scenario increasingly less likely, which is good. There is another reason why the very high scenarios have some inconsistency in them, and that is none of these scenarios considers the feedback, and I think that was also part of your written question, the feedback of climate change onto our economies. So if we are living in a dystopian world with lots of bushfires and floods, and our economies just crumble under all these impacts, then at some point also our emissions could potentially go down, unless we are really good in burning fossil fuels. And so that feedback is also not considered there. So therefore, yes, you're right in your question. RCP 8.5 is a dystopian world. It's a worst end scenario. It's not completely implausible. If we rewind a lot of policies, if every nation in the world would be governed by somebody like Trump, with putting extra hurdles in the path of renewables, then we could see that. But at the moment, it doesn't look likely. Does that answer your question?
Yeah, I suppose it does. Thanks.
Good. Let's go to, there is a next question. Oh, there are now many questions coming up. Very good. I just take them here as I see them. Dan, could you ask your question? Dan Swartz.
Thanks, Malte, and thanks all for that very interesting presentation. I'm glad you put up that last upcoming work, Jared, because my question was going to be, can you do this at a regional level? Because obviously that becomes much more decision relevant. And now that I know you're doing that, I'm very curious to know what projections you would use for that. And I don't know which regions of Australia or the world you're thinking of doing it for.
Yeah, so there's obviously a number of different ways of deriving or coming up with regional projections. A very simple start would be expanding a pattern scaling approach to use not just drivers of like annual mean, global mean, surface temperature as a predictor, but also these regional disaggregated. So we could, in theory, deal with just the 58 or 60 different regions and come up with down to scale projections at the regional level. And then obviously that's a relatively simple process. And then there's obviously a much more complicated process going from 50 different bits of the globe to a 10-kilometer daily projection. So to answer your question, the simplest one would be, first of all, coming up with the 6 different regions and applying a pattern scaling approach, which is already in the literature. So it's kind of just, that isn't necessarily, that's kind of something that we're looking to do in the very, very short future as, yeah.
Thank you. And some of our earlier work is also, you find it on different web resources already. But let's go to the next question. Alan Barley.
Hi, Malte. Thank you for the opportunity and fabulous presentation for you 3 guys. It's really wonderful that we've got this work going on in Australia on behalf of the planet. So thank you for the work you're doing. I've just got a quick one, and that is, Malte, you mentioned rather briefly results out to 2300, which sounded very alarming indeed. Can you elaborate on the range of uncertainty of such long-term projections as those, and what the likely regional impacts on the habitability of the planet might be if we actually ever ventured into that territory?
Yes. So what I showed there was the raw CMIP6 output for this high-end scenario that I mentioned, and there different climate models project anything in between 6 degrees maybe warming to 17 degrees warming, and yeah, that would be a very, very different planet with 17 degrees warming. I wouldn't say it as a whole it becomes inhabitable. I wouldn't say that the human species is going to go extinct, but it would change the planet's face unrecognizably towards today's world, and would come with tremendous hardship and millions of people severely impacted or dying. So yes, it is a dystopian world. One additional thing that has to be said for these very high climate projections of up to 17 degrees, they come from models that have a very high climate sensitivity, what Zebedee briefly showed there, of 5 degrees or higher. We have multiple paleoclimatic evidence lines and energy budget constraints that make us believe that these very high climate sensitivities are in fact less likely than what it appears to be from the raw CMIP6 output. So therefore, the high warming scenarios at the moment with the best available science are slightly discounted as not so likely. They do very well on a lot of metrics and observations, but and we can't exclude that high climate sensitivity, but in the we wouldn't say this is the most likely projection. So in summary, it's the warming projections from high-end warming scenarios for, at the moment, very high-end and low likely scenarios. So we are not going to see that, and I would bet my money that the world is smarter and goes down to 2 degrees or maybe even 1.5 degrees in the near future. I hope that answers your question. We had a similar question before, but I will, Alan, is that okay?
Yep, that's fine. Thank you for that. Appreciate the answer.
Okay, very good. There was a similar question here. There's one by Januka, which has a different line. Januka, do you want to ask your question?
Sure, Malte. Thanks for this fantastic presentation. I think this is a really nice resource for us as teachers as well. My question is slightly different from science. It's a perception of associating with a financial giant. Do you foresee any conflict of interest when you partner with the financial giant? I mean, this argument has been made against other sciences as well. How would you cope with that?
I think it's a very good question. My answer would there be, in order to create the change in the world, to move the world away from fossil fuels and to have a chance of reaching 1.5 and 2 degrees, it is really an effort that has to go throughout the whole society. And that includes large corporations, that includes hedge funds, that includes those who put with their money, invest in sectors that are either more or less worthwhile. So therefore, providing the best available scientific information to those who make the billion-dollar decisions, I think is in part a duty for us climate science, as much as it is to talk to the public, to the general public. But investment decisions are not smart, are not climate resilient, and are not in those areas, sectors, for example, that would flourish under a zero emissions world. If we have continued wrong investments, then we are going to have stranded investments in the future. And that means stranded investment means a lot of incumbent interests to not change the course that this world takes. So therefore, I completely see your point about either being in bed with large mining giants who also have some coal assets as their part, or financial industries that have some fossil fuel interests potentially there. However, I think it is also as part of the TCFD, the Task Force on Climate-Related Financial Disclosures, is the responsibility of every board in Australia and globally to factor in climate impacts and to look at the energy transition in the future. And therefore, we as climate scientists ought to help them with the best available information. If you look at the information that is out there at the moment, it is often rather rudimentary and about 10 years behind to what climate science actually has to offer. So therefore, we made the decision to partner with those. Is that a satisfying answer? I love you. I'm happy for you to be more critical even in your reply.
No, that's perfectly an acceptable answer. I think it comes down to trust, isn't it? How much trust can the public place on scientists when they partner with financial giants or whatever, whoever the people that they partner with? I think one way to circumvent this negative perception is to show uncertainties, which people don't really talk about, and that's what I think you guys are doing really well with this platform, showing uncertainties in projections. And I think that helps, gap that distrust, make that gap narrower in the public's eye, I think. So that's a fantastic move that you've taken.
Thank you. Now let's go to the next question. And sorry, there are many more questions, and I appreciate for all those who have been here today. We have a seminar again coming up. We can share that maybe again in the chat for those of you who have to leave. Otherwise, Jared, myself, and Zebedee are happy to stay on a bit longer to go through your questions. So I will now give the word to, next in my list is Tom Yankos.
Hi, Malte. Thank you very much, guys. That was a fantastic presentation. Must admit, a little bit over my head, but still interesting nonetheless. Really interested in, Malte, as you mentioned, there's a requirement for TCFD and a lot of organizations that we're dealing with at ClientWorks are interested in the physical risks through various different stimuli. So interested to know how autonomy has used the tool and if there's scope for, and what scope there is to apply the types of tools that you've developed to these types of decision makers going forward.
Yes, thank you, Tom. So two parts to your question. Autonomy is first using that tool, I believe, as a public outreach tool, but also to further the general understanding among themselves and their clients about where the future is heading, whether we are heading in the next 10 years to 4 degrees, or whether with mitigation we are going back to 1.5 degrees in the next decade, or whether it's all slightly more narrow band and the scenario differences really pan out in 2030, 40 and thereafter. So I think that general understanding is the first key part. However, given how closely related global mean temperatures are to regional temperatures and also regional extremes, getting a grip on the best scientific modeling of the uncertainties in the global mean temperature gives you the best foundation to calculate your regional extremes and the regional temperature changes. So I think, therefore, it's a pivotal starting point for any further analysis. And what we see often in the TCFD space at the moment is that just some single model or system results are used, and then it says here, I mean, CSIRO put out fantastic resources in the past, but I think for TCFD, you really want to have the probabilities at the different locations and to map that with your assets in order then to have a vulnerability risk of your asset and to map that with what are the probabilistic climate change projections at a specific location. So I think there's ample room. I was part of some of the probably now most used probabilistic projections for the US, where every county, etc., is mapped and gets its probabilistic climate impact projection. And we are working on that to do that also globally.
Great, thank you.
All right. So now next on my list is Julie Arblaster. Julie, wait, I just have to find you here. And hello, Julie, it's nice to hear you. Wait, if you're happy with it, I can also promote you as panelists. Oh, no, that was not a, you're back there. Hi, Julie.
Hey, Malte, how are you? You can hear me?
Yes.
So yeah, my question is, you've developed these wonderful tools for looking at the projections of physical climate. Just wondering if you can use them to back out allowable emissions for different sectors in terms of, yeah, maybe more certain types of industry that are consistent with the scenarios at a more local kind of nationalistic level.
Yeah, thank you, Julie. And for everybody who doesn't know Julie, Julie is from Monash University, and I should have asked everybody to introduce you quickly, but Julie is really the master of CMIP analysis. I think nobody has ever had more publications on CMIP analysis than Julie. So thank you, Julie, for joining. For the as you know, to break it down into what are permissible emissions for the sectors, you can do that on a pure working group 1 basis, the geophysical science basis. You can do that globally. And then the big question is, how do you break it down to nations and how do you break it down to sectors? And there are lots of value judgments along those lines, or beliefs into whether you follow the cost optimal approach or what you use. So first, on just a global step on breaking down permissible emissions. Yes, we looked into that together with Chris Jones and Sönke Zehle and others a bit, and Charlie Coben. And so it looks like that our CMIP6 CO2 concentration projections were slightly on the high side. In the CMIP5, we were slightly on the low side. Now we are slightly on the high side, which means that the permissible emissions backed out from the ESMs are slightly higher than what we had originally in MAGICC. So that is the first point, but this is a small part. Then to break it down into nations, obviously you can do 2 approaches. You can do what the integrated assessment model says, what is a globally cost optimal approach, and what would be implemented if you had whatever initial allocation of emission rights, but then full carbon trading, so to say, so that the cost optimal solutions would be pursued by the market, which of course is not going to happen. So our best guess for going to the question, what you say, is to really look at the integrated assessment models, what is done in the different regions. They largely work by larger regions and in the different sectors. And I mean, clearly what we see is the electricity sector is to decarbonize first. And there's no question that Australia's approach that was in the headlines a year ago, so about a 28% target for the electricity sector, whereas we have a national target of 28%, is a really stupid thing to do, because you have so much lower cost options in the electricity sectors compared to agriculture and some industry parts. And yeah, if you combine the chain of, we have for the special report for 1.5, we have about 400 scenarios. Now for the AR6, we are going to get around 1,000 scenarios. If you combine that with a geophysical assessment of what are your permissible emissions, then you can make pretty good ranges on the different sectors and the different regions, but there's a lot of work to be done. I don't know, there was a little bit of waffling. Maybe Zebedee and Jared want to add here?
Yeah, do you intend to do that, I guess,
yes,
as part of this? Yeah.
Yes, not as part of this in the next 1 or 2 years, yes.
Okay, great. Thank you.
Next on my list, I see here, we have still a few people with us. So I go to Peter Christoph. Hello, Peter, and I promote you to panelist. So you will quickly move out and back. Yeah, Peter. Briefly introduce yourself, and I think you have to unmute yourself. There you go. Briefly introduce yourself and then your question.
Always terrifying to be seen. Peter Christoph, I'm in School of Geography. Look, this is a fabulous presentation and the model is terrific, so very, very grateful for all of that. Just a very quick question about methane, uncontrolled methane release, and the extent to which that's factored into the modelling and how that plays out. So very quick comment on that would be useful.
You mean the fugitive emissions of gas exploration, or you mean the permafrost and clathrate emissions?
More the latter, permafrost.
Yeah, so in terms of the permafrost, we use, I'm talking too much. Maybe I hand over to Zebedee.
Okay, sure. So there's 2 parts to this. So one is the runs we've just shown are all concentration driven. So all ESMs run with prescribed concentrations. So in that case, the permafrost and the clathrates are not included in the kind of temperature projections. But what we do when we actually do scenario assessments, so say we have an emission scenario where we start from emissions rather than concentrations, then we will include the feedbacks from both permafrost and clathrates. And so we take it into account, and what we generally find is that in line with a lot of the literature out to 2100 under kind of mitigation scenarios. There are some feedbacks, but not enough to cause really rapid runaways in the median. Of course, at the high end, you have much bigger concerns, and that's always the concern, is the really high end. So we're able to explore some of those feedbacks. For example, a high end methane or cleft rate response with a high end climate sensitivity, and you see them kind of really send each other off into really high warming. So we're able to capture that. But, and then in the longer term, obviously it makes more difference. And the further out you go, you see this kind of slow, or relatively slow, sometimes faster release. So we have it all in there, and we do some exploration, but that's another key part for us, that we want to try and take some of the more recent literature and explore what that says and what the implications of that would be when you combine it with everything else in our probabilistic distribution.
Yep. Terrific. Thank you.
Cheers.
Thank you, Peter. Now I give the word to Sean Walsh for a question about. Sean, are you there?
Yes, thanks for that. I think you've partly answered my question already. It was really, I guess, getting into the spatial detail, but I was looking at it perhaps in a different approach, rather than trying to do separate downscaled models for each region, trying to see if there was a way of looking at the entire globe. So this would be maybe something like a spectral approach. We're trying to understand the connectivities.
Can I briefly ask you to introduce yourself?
Oh, my apologies. I'm a PhD student, ecology, in fact, but my background is mathematical modelling. So I'm not a climate expert as such, but I guess I think about complex systems. So yeah, I'm just trying to understand whether it's possible to look at like a broad mathematical approach to the spatio-temporal patterns, rather than treating each climatic region separately.
Zebedee, do you want to take that, or should I?
Do you want to start? So I'm also half typing an answer to Alan Barley in the chat at the same time.
Okay, Sean, absolutely. Now that the CMIP6 models are getting to finer and finer grid scale, there's absolutely the room for doing something that is globally valid, rather than going into the CMIP6 and then Codex, which is the regional downscaled models approach, where you have something by region by region. Codex still has these high resolution regional models that still have a lot of value, but I think we're getting into the area where we can do really valuable stuff with the global models, and then if we know the global mean temperatures, for example, and we know certain other parameters, then we can infer probabilistic climate projections for the regional scale. And the way it works, like for temperature, is relatively simple, because across the line, if you look at the CMIP6 models, the spatial patterns of temperature are very constant. Like there's a little bit of movement there if you go to long-term equilibrium scenarios. If you then were to use, instead of global mean temperatures, if you were to use the land temperatures, then you have an even more stable pattern of temperature. Of course, there's a question of how do you capture then the heat extremes, etc. But even those, they scale relatively closely. It's a different story for precipitation. And for precipitation, there you have two other compounding impacts, which is, the one is the aerosol cooling, and higher aerosol emissions normally cause a lowering of the precipitation. And then you also have the vertical energy balance of the troposphere, which determines your precipitation. So there the story is a bit more complex. In the history, we saw a slight dip in precipitation in many regions. However, under continued warming, we're going to see that increase. But there, the constant linear approach doesn't work that well anymore. Zebedee, do you want to add?
Yeah, the one other thing I was going to say is your question about the spatio-temporal patterns is a really important one. Which, as Malte said, is why the constant downscaling approach seems to fall over. And it seems to be really important in the strong mitigation scenarios. So if you're not looking at a 4 or 5 degree scenario, but at a 1.5 or 2 degree scenario, that's what you need to take into account. And there's a lot of work being done by Leah Boysch, who's at ETH Zurich, and I'll put a link to her paper in the chat, trying to create an emulator that actually has those sort of spatiotemporal patterns in the background. And she's done some great work in the high emission scenarios, and then there's some ongoing thinking to be done about what happens in the strong mitigation scenarios.
And unfortunately, if it weren't for COVID, Leah Boysch would also be sitting with us in Melbourne for this month and for a half year as a guest. However, without closed borders, that has to be deferred into the future. So are there lots of questions in the Q&A chat have been answered by typing. If you have additional questions or comments, just raise your hand and I can give you the word. Last chance. No, so I think then we are good. Thank you so much for the participation today, and work through or have a look at the resources if they're useful for either your research work or other work that you do. We would love to hear from you again, and have a safe, enjoyable future here in Victoria, where we can now enjoy the outdoors a little bit longer. Or if you're in other parts of the world, we are very sorry for the lockdown, but after 4 months of lockdown in Melbourne, it pays to sit through it. The world is good at the other side of the tunnel. And 2021 is going to be a fantastic year now that we have a net zero commitment from the Biden-Harris plan. We have Chinese tremendous net zero 2060 targets, and we have South Korea and Japan putting net zero targets on the table. So 2021 is going to be very different to 2020. With that, we are looking forward to see you in one of our future seminars. Jared, could you share the last slide for the next seminar that is going to take place? Yep, that is for those who code. There was
trade secrets.
Yeah. So what is a human-centered electricity system? It's on Wednesday, 25th of November, and have a look on the Climate College Unimelt seminars page. With that, thank you very much and all the best.